Let's talk about how to find the length of an arc that's a portion of a circle. It's conventional to label an arc that's not the whole circle with the letter S. The whole circle, of course, has an arc length that is the circumference. The circumference of a circle is 2 pi r. Of course, that assumes that you know what r is. In the case of questions that you're actually asked to compute the arc length or find the radius or the angle, you'll be given specific values for at least some of those variables. But at the end of this video, I want a formula that lets me do that for any r, any theta, and any s. So I'm going to keep things very general. I'm going to use the generic r for radius, s for arc length, and theta for the angle, at least until we build our formula. Then we'll go back and do a couple of examples. An important feature to remember here is that as long as our angle is in radians, what we have in S is the number of radiuses, or the number of radians of length, carved out by the angle theta. In other words, S is theta times the radius. Let's just think through that again. Because theta is in radians, and only if theta is in radians, then I can just say that the distance between one point on my circle, let's call it A, and another point on my circle, let's call it B, the distance between A and B around the circle is the number of radiuses carved out by theta. So S, the arc length, is the radius times theta. It's actually a bit more common to see this formula written as S equals r theta. This is the one that you need to have on a note card, on a formula sheet, or memorized, depending on your particular situation. The most important thing to remember when using this formula is that theta has to be in radians, because that's how we got this formula. Remember, we said that theta was in radians, and therefore we can build the formula S equals r theta because the length S is the same number of radiuses as theta. It's equal to the radius of the circle times theta in radians. Let's move our formula out of the way for now. I'm just going to put a copy of it up here, and I'll erase the other one. And now we can talk about a specific example. I can show you now how to find the arc length of a specific circle if I know the radius of that circle and the angle theta. I can also use this formula to find theta if I know S and R, or to find R if I know S and theta. I'll do one of each of these, but let me just start with the most basic. Find S if you know R and theta. Here's an example of a problem like that. Find the arc length S that subtends an angle of pi over 6 in a circle of radius 7 meters. Now, the first thing to recognize here is that the word subtends is perhaps new to many of us. We just say that S subtends theta, or an arc length subtends an angle if the angle cuts off that arc length. So imagine a circle, and imagine an angle in that circle, and recognize that this arc length right here is being cut off by this angle right here. We say that S subtends theta. Alternatively, you'll sometimes hear that theta is subtended by S. It's a really weird word, and I kind of have a hard time wrapping my head around which way the definition is supposed to go. So I don't really worry about it too much, except to realize that S and theta have this relationship. Theta cuts off an arc length of S, and subtends just means is cut off by. So since we want to find an arc length S, and we know our radius, and we know our angle, we literally just need to plug those values into this formula. In this case, S is going to be equal to 7, because that's my radius, times theta, pi over 6. When I do this multiplication, I get 7 pi over 6, and that's my answer. That is the length of the arc cut off by an angle of pi over 6 radians if the circle has a radius of 7 meters. Of course, the circle has a radius of 7 meters, so I should be careful here to include a unit. If the radius of a circle is in meters, then an arc length is also going to be in meters. This is a linear measurement here. It doesn't really seem like it because it's not on a line. But if you imagine walking from the center of the circle out to the edge of the circle, you'd be walking in a straight line. You'd be walking in one dimension. You could only go forward or backward. If you had to walk along the edge of the circle, you could also only walk forward or backward. So we consider this also to be a linear measurement. Therefore, since my radius is given in meters, my arc length will also be in meters. I'll add that to my answer and then put the box around it. That's better. Now, for those of you obsessed with decimal approximations, this works out to be about 3.665 meters. Sometimes decimal approximations are more appropriate. In purely mathematical settings, it's common to leave your answer as an exact value. If the situation calls for it, of course, you can convert that to decimals easily just by putting that value into your calculator. I tend to ask my students to leave their answers in exact values. If a student gives both of these answers, then I'll give them credit for the exact value because it is there. But I'd rather see that and the decimal approximation rather than just the decimal approximation. It depends on your teacher, it depends on your course, and it depends on your reason for doing this problem in the first place. Okay, I've changed this problem just slightly. Instead of an angle in radians, I'm now being asked to find the arc length that subtends an angle of 45 degrees. The circle still has a radius of 7 meters. So the change that I've made affects the angle in two ways. First of all, it's a different size, and second of all, it's measured in degrees instead of radians. We can still use the same process. We can still use the same formula, S equals r theta. But as I start to plug in my values, I have to recognize that theta is not currently in radians, and I have to convert it first. So I'm going to go over here, kind of to the side. You might do this on scratch paper. You might do it in the margin. And I'm going to take my 45 degrees, and I'm going to convert it into radians. So this is one of the reasons we had you do this earlier. Effectively, what I want to do is get rid of the degrees and introduce radians. But I can only do that if I multiply by 1. So I'm going to multiply by 1 in the form of radians over degrees. That conversion factor is pi radians is 180 degrees. So having written out this conversion, I can actually do the arithmetic. It might not be super obvious that 45 goes into 180. It wouldn't be obvious to me. I only know that because I've worked through this problem. If it's not obvious, just find something that is. For example, I know that 9 goes into both 180 and 45. 9 goes into 180. Well, 9 goes into 18 twice, so it goes into 180 20 times. And 9 goes into 45 5 times. I can now see the more obvious fact that 5 goes into both 5 and 20. 5 goes into 5 once, and it goes into 20 4 times. Perhaps a more important observation here is that the degrees symbols cancel as well, just like in chemistry, and that's why we use this conversion factor. Let's tidy that all up. What I now have is 1 times pi in my numerator and just 4 in the denominator. So instead of plugging in the value 45 for theta, I'm going to plug in pi over 4. Now that I've done that, I just need to do the rest of the arithmetic here. S equals 7 pi over 4. S is a linear measurement. The linear measurement in this problem is meters. So my answer is also in meters. Okay, let's take a look at what happens if we have different pieces of information, and we kind of need to flip this formula on its head a little bit. Find the radius of a circle whose central angle of 2 pi over 3 is subtended by an arc length of 2 centimeters. Okay, so there's that word subtended again. Remember that an angle is subtended by an arc length. An arc length, S, subtends an angle. Here we have an angle being subtended by an arc length. So that means that the angle is cutting off the arc length, or cutting out the arc length. Equally, that doesn't really matter too much because we know that the relationship between these things is S equals R theta, and we know our S, the arc length is 2. We're looking for R, and we know our theta. It's 2 pi over 3. Multiplying both sides by the reciprocal of this fraction to isolate R, gives me this arithmetic, and I'll just simplify, canceling my 2's, canceling the fractions on the right hand side, and that gives me R equals 3 over pi. As an exact value, that's my answer. Let's turn it around a little bit. 3 over pi, because I need to add a unit here. The arc length, which is a linear measurement, is given in centimeters. So that means my radius is also in centimeters. Okay, I've changed this problem a little bit too. This time let's find the radius of a circle whose central angle of 190 degrees is subtended by an arc length of 2 centimeters. So the distance we're going to walk around the circle is the same, but it's a different angle size, and so we're going to end up with a circle with a different radius. Not only is the angle size different, it's in degrees. So I can start to set up my formula here. S equals R theta. I know my S, it's 2. I don't know R, that's what I'm looking for. And I do know theta, that's what I want to plug in here. But theta is given in degrees. So once again, I need to convert between degrees and radians before I begin. So I'll cancel my degree symbols. And this time I have a common factor of 10, so I can cancel these zeros. 19 and 18 don't otherwise have any common factors, so I have an angle size in radians of 19 pi over 18. That's not a very nice angle, but that's what it is, and that's actually more common than not, so that's what our problem's going to look like. Okay, let's simplify by multiplying both sides of the equation that I've created by the reciprocal of the fraction that I need to get rid of. I need to get rid of it on the right hand side because I'm trying to solve for R. That means I can cancel both of those quantities. This is 2 over 1, not 1 over 2. So I can't cancel anything there. Ultimately I have 2 times 18, which is 36, over 19 pi equals R. And if I turn that around a little bit to give myself some more room, I have R equals 36 over 19 pi centimeters. Again, this is easy to convert to decimals just by plugging it into your calculator. But I find a lot of videos out there do that, or they do a lot of the work in decimals. I want my students to use exact values as much as possible. So one of the reasons for this video is to give you examples of problems that are done in exact values. Okay, we've done problems where I knew r and theta and I was asked to find s, both where theta was given in radians and where it was given in degrees. And we've done problems where we knew s and theta and we were looking for r, with theta in radians and with theta in degrees. So now let's take a look at an example of a problem where you know s and r and you're looking for theta. Find the angle theta subtended by an arc length of 7 pi inches in a circle whose radius is 6 inches. Here's my formula. S equals r theta. This time I know s, which is 7 pi. Okay, it's 7 pi inches. Let's throw that unit in there as well. Equals r theta, and r is 6 inches times theta. And theta is what I'm looking for in this case. Now think about these inches as factors. Then in the same way as we can cancel units in chemistry, we can cancel them here. So now I just have 7 pi equals 6 theta. Now of course I could have written it that way to begin with, but I wanted to make the point that in the case where you have two lengths with the same unit, those units can cancel. And that's why we get away with writing a problem like this without any units. Let's finish this out. What I'm looking for is theta, so I'm going to divide both sides by 6. 7 pi over 6 does not reduce, and I just have 7 pi over 6 for my angle theta. Now what I've been doing is turning the equation around so that I have my variable here on the left-hand side, and the right-hand side has the value for that variable. And then I've been adding the name of the units at the end. But in this case, my units would be radians. And while it's not wrong to write that, remember that radians are effectively a unitless measure. So we don't technically need to write the word radians. It's understood and it's implied. So either of those answers would be correct. One thing I would like to point out is that my answer is very much in radians. It can't be in degrees because the formula that I've been using, S equals r theta, assumes that theta is in radians. If you have any questions at all about this video, please leave them in the comments.